Welcome to our Network Plus course, and we're going to start with the TCP/IP basics. My name is Robert McMillen. You see my contact information on the left-hand side. I started my career as an IT administrator for a manufacturing company after college and earning my first CompTIA certification, and that was the A+. I quickly learned how to fix and troubleshoot desktops and laptops. My real passions were networking and server administration. I earned my first MCSE and Cisco CCNA shortly after that, and I've continued with various certifications over the years to now include over 50. I started a successful consulting company in 2001 and eventually sold it in 2017 to focus on teaching networking and security in college and being a video and book author. We've got a lot to talk about in our first section. We're going to talk about what's an IP address, go through lots of IPv4 structure, and then we're going to get into the heart of the Network Plus test, which has a lot to do with TCP/IP and how to manage it. And then we're going to move on to broadcast information and the OSI model. You may have heard about the OSI model and how it travels from one computer to another and all the different places it stops along the way. And this is a section that will be covered in detail in our Network Plus test. So let's start out with what is an IP address. It's a unique string of numbers, and that's separated by periods, and it identifies each computer using the Internet Protocol to communicate. IP is a separate protocol from TCP, UDP, and others. It allows communication between two or more computers. It's not just the way we communicate over the internet, it's also the way we communicate in an office or home where there's more than one computing device, and that can include a PC, laptop, tablet, or phone, and other devices as they're invented. They all use an IP address to communicate. If you wanted to communicate with someone at school or work, you would both have to speak the same language and not have a wall between you. IP addresses work the exact same way. So if PC number 1 wants to communicate with PC number 2, they need to both have an IP address, and they both have to be on the same network, or in this example, be in the same room. To leave the room, you have to have a doorway called a router. A router can route you to a place where you can talk to computers outside your room, such as a telephone can do. It's your router that allows you to talk to other people that are not in the same room as you. Let's give some examples to help you understand those different concepts. Let's start with IPv4. So here's an example of an IPv4 address. Most computers use this type of address, and it will be the one we focus on for this course. In order for me to communicate at this address with your computer, my first 3 sets of numbers, called octets, need to be the same. The last set of numbers need to be different. The first 3 octets are the same, but the last one is different from the IP you see here. So if all our numbers were the same, then we would not be unique. And uniqueness is a requirement for us to communicate. But for now, just know that the subnet mask separates the networks from the hosts. To use our example, this means that the first 3 octets represent a single room. The host in this case is .1, and that represents a person. There can only be one .1 person. The next person can be represented by .2 and so on. As long as we're in the same room and we have unique names, then no one in the room will have a problem communicating with us or each other. Now let's look at an example of IP version 6. There's a lot more addresses available for version 6 than version 4. We ran out of version 4 addresses on the internet, so we came up with version 6 so we could continue to have more addresses. So why haven't we completely switched over to version 6? Well, it's because it's harder for most people to figure out. And when we came up with a temporary solution so we could use version 4 inside our homes and businesses while version 6 was out on the internet. Did you know there's more than 8 trillion addresses per person when we use IP version 6? We shouldn't run out of IP addresses anytime soon. And IPv4 is a subset of IPv6. They're not completely separate. IPv4 sits inside of IPv6. So you could translate all of the IPv4 addresses into version 6. Let's go more into detail about the IPv4 structure. IP version 4, also known as the 4th version of the Internet Protocol, is the core protocol that routes most of the Internet's traffic. This is a connectionless protocol, which means that the state of the connection is not preserved, and the data that's transmitted to the receiver is not ensuring that the recipient is available. Well, without any kind of insurance, then we need to make a change. We need to add another protocol to it. IPv4 uses 32-bit addressing, which allows a total of 4,294,967,296 addresses. So that basically means it's 2 to the 32nd power. If you use your calculator on that, you'll know exactly that that number is accurate. An IP address consists of 4 octets, and those are separated by a period, which is also known as a dotted decimal notation. For example, the IP address 192.168.0.1, as we showed in the previous video, represents 4 octets. And you see these represented by the 3 X's separated by the dots. So we could spell out 192.168 and then all the zeros, but we can shorten it to what you see here. Either one of these are correct. However, the shortened version is a little bit easier to write out. So what do the numbers represent? In the 1950s, many different scientists created their own language, also known as a protocol, and that allowed their computers to talk to each other. Well, it made things really confusing. Later on, Microsoft, Apple, Novell, and lots of others, they all created their own protocols too. And no computers could talk to each other except their own brands. Finally, the United States Department of Defense came up with the perfect protocol, and they paired it with a connection-oriented protocol and called it Transmission Control Protocol over Internet Protocol. And it was invented for 2 reasons. First, so computers could communicate with each other regardless of brand and model, and the second was to allow the DoD to launch nuclear missiles at an enemy target using the phone system. By the 1950s, the phone system was so widespread, it was like a spider web. There was no way any group of attacks could take out the entire thing. So scientists came up with the perfect way to launch a nuclear device without anyone being able to block it. For those of you who used the internet prior to 2005, you might be aware of using a dial-up modem. And even though we were using a dial-up modem, it was still using TCP/IP to go browse the web. Eventually, the Cold War started to subside, and the government decided to give away the technology to various different companies and then eventually to the public to increase the economy and create a new industry. The information age was born on that day. Let's talk about counting in binary. The IPv4 addressing is made up of 8-bit octets. Our IP addresses are made up of these 8 bits, and you can see a representation here. They can all be 1s, or they can all be 0s, or any combination. Can't be anything else. These 1s and 0s have decimal numerical equivalent values. Let's break that down. The number 1 on the right-hand side now is represented by the binary number you see here. It can be a bit confusing, but the numbers add up from right to left, not left to right. Let's take a look at this further. So if we see the number 2 in decimal, in binary, we go from the right to the left. So the value of the first octet is 1. The value of the second octet doubles to the value of 2. I'll bet you can imagine what comes next. Here's the number 4. It's 3 spots over. So we've gone to 1, 2, and 4. You keep doubling the value every step to the left until you get to a top value of 128. If you add all those together, that's the same as 2 to the 8th power. 8 bits is 2 to the 8th power. If you add up all these numbers, you actually get to 255. Well, why wouldn't you get to 256? Well, that's actually a really easy answer. It's because we start with the number 0, and the maximum number goes to 255. That's a total of 256 digits, although you only see 255 in the scale. If we started at the number 1, we could have gone to 256, but scientists thought it would be confusing to not start with 0. They were, of course, wrong on that part. These types of questions will be on lots of tests at school and certification tests like the Network Plus and A+ exams that many employers are looking for in potential candidates. Here's another representation of converting decimal to binary. If we see on the right-hand side, we see the number 1, and then it doubles all the way through 128. Yet at the top, we don't see anything other than the 1s. The value of 0 is always 0, And it doesn't matter which slot you put it in. 1 through 8, it's always 0. However, the number 1 does change value depending on where it is. All the way to the right, it's the number 1. Then you keep doubling until we get to 128. Once again, that's 2 to the 8th power. It equals 256. However, we only go up to 255 digits, and that's because we start at 0. Let's take our last graphic showing all of our binary ones in order and our values underneath them, and we can see that IP addressing is made up of a 32-bit number. And this isn't important yet, but it will be soon. So for now, let's learn to count in binary so we can apply this knowledge to upcoming lessons. An IP address is split into 4 octets. Let's look at one of those octets, and we see an octet is made up of 8 numbers. And if we add them all up, starting with 0, we get to 255. If we once again use the number 1 all the way to the right, the value is 1. Now we come to the value of 3. So really we can get to any number, even or odd, because of the fact that our very first number is an odd number. So all the other numbers are going to be even, 2, 4, 8, etc. But the first number is a 1, and because it's an odd number, that allows us to come up with any combination of numbers that we need. So to get to 3, we see all the way to the right, the value is 1. The next value over is 2. 2 plus 1 equals 3. So how do we get to 6? Feel free to pause the video at any time and write this out on paper and see if you're right. Now we're going to do the number 6. Let's go ahead and take a look at that on our graph there, and we see 6 can be added up with 4 plus 2. So it looks like the 2 on the end and then leave the number 1 off. And there it is. So from right to left, it's 0, 1, 1, and then the rest are zeros. Let's try the number 129. Now you'd think that that would be a tough one, but if you look at the scale, you see that 128 is all by itself, so all you have to do is just add 1 to it. And there it is, 129, 1 on each end. Let's do one more. Let's do the number 67, which truly is a little bit more complex. So 67, you want to make sure you use the number that's closest to what you're trying to get to without going over. That is the trick. So the number closest to 67 without going over is 64, which is our second number in from the left. And then go all the way to the right, and you'll need to add in 3 more digits. And you'll end up with 67. And there it is. That represents 67. Now let's go over and do the opposite. Let's choose to convert decimal to binary. Eventually you're going to be able to do this in your head, and it will make your networking job much easier. And it certainly did for me. After doing this for so many years, I was able to convert this all in my head, and I know you'll be able to do the same thing after just a little bit of practice. So we're going to start with the number 42. If we take a look at our scale to the left, we can see what number is closest to 42 without going over, and we see it's 32. And they just need to add in the difference. And there it is. 32 plus 8 is 40, plus 2 is 42. And here's 16. Now 16 is all by itself. So if you need to get to 16, that was a really easy one. You just do the first 3 zeros, a 1, and then the rest are all zeros. So once again, look at your scale. Now let's do 7. What's closest to 7 without going over? Well, that would be a 4. And then we just need to add in a 2 and a 1, and that will give us 7. So from the right-hand side, we go 1, 1, 1, so that's 1 plus 2 plus 4, that equals 7. Now let's do 192. You might have to get your calculator out for that one. So 192, remember, what's the closest we can get to it without going over? That would be 128, and we just need to add up the difference. And there it is. The first 2 numbers in our octet add up to 192. I think you're starting to get this now. So you're learning to count in binary and convert from decimal to binary and binary to decimal. Let's talk about subnetting, or how we separate a network into subnetworks. Well, let's first talk about what is a network. A network is made up of a lot of different hosts that all can communicate with each other. So a host would be a PC, a tablet, a phone, lots of different devices. That's also referred to as the endpoint because it's the last point in which a network connects. So we see an accounting, an HR, and an IT network. They're all connected to a small switch, and that small switch is connected to what we sometimes refer to as a core switch, and it could also be a router and it could be a layer 3 switch. And a lot of that is kind of confusing, but it'll all make sense in a little bit. But we need to have a router or a switch with routing capabilities to separate networks that are on different subnets. You can see the accounting subnet is a different subnet than the HR and the IT. How do we know that? Well, we know that because of binary. Offices sometimes will split up their networks into multiple subnets to avoid what's called broadcast traffic. And that's where computers all try to find each other using the broadcast address. By separating these networks into subnets, sometimes referred to as virtual LANs when you use a switch to do it, we can cut down and block all that extra chatter. So our first network is 192.168.1.0 and it's a /29. What does that /29 mean? Well, it refers to classless interdomain routing, and we talk about it a lot as CIDR. CIDR just makes it easier for us to refer to what you see here, which is a subnet mask. And in this case, it's a /29 subnet mask. So if you see a slash and a number after it, all it's referring to is the subnet mask. And all the mask does is it splits the hosts off to the right and the network off to the left. No matter what, all these numbers have to add up to 2 to the 32nd power. And you see them split up into 4 different octets. 4 times 8, 8 for oct, equals 32. And the decimal number that matches 2 to the 32nd power is over 4 billion. So we're either going to have a lot of hosts on the right or a lot of subnets on the left. One of the two. It's a sliding scale. In this case, our /29 has a value. So we see that it's the last 3 zeros are set for the hosts. All the zeros represent the hosts, and on the left-hand side, all the ones represent the network. Now, this is not the same as adding up binary, where you could have ones and zeros all spread out over the 32-bit address. This has to do with the mask, the subnet mask, the thing that masks out the hosts from the networks. So all the numbers have to be contiguous. You have to have all ones in a row or all zeros in a row or a combination. It can't go 1 0 1 0. And if we add up the values 1, 2, and 4 underneath our 3 zeros, we come up with 7. So we add up those last 3 bits. So how do we know how many usable addresses if we add it up using binary? Well, that's 7 addresses minus 1 because 1 is used for broadcast. Remember, we talked about broadcast going out to find all the other computers. Every computer sends out a broadcast packet, and it does it on its last available IP address. So 6 are usable. Well, let's say we don't want to use binary to add these up. So there's 2 different ways to get to the same usable IP addresses of 6. One is to add up the binaries I just showed you, and the other is to go to the power of 2. So 2 times 2 times 2 equals 8. So now instead of subtracting 1 for the broadcast address, however, we need to also deduct 1 for the network address. So 8 minus 2 equals 6 usable IP addresses. So either way, you don't have to do it one way or the other. You can do it any way you want. However, on the Network Plus test, if you're presented with how many usable IP addresses there are in 2 to whatever power it is, then you'll have to subtract 2. However, if you're shown a grouping of binary numbers, you just subtract 1. So in this case, let's spell it all out. 192.168.1.0, 0 is our network. Then the numbers 1 through 6 are our usable IP addresses we can assign to our PCs and our phones and our tablets. Then the number 7 we can't use for anything because it's going to be used by default as the broadcast address. So the next subnet, so if we go from accounting to HR, for instance, the next subnet starts at .8 because we've already used 0 through 7. So once again, the first address is unusable because it's our network address, .8. .9 through 15 are our usable addresses, and .16 is going to be our broadcast address. So we would start the next one after that at .17. How do we separate these 3 different networks? Well, we can use a router because a router is designed to separate differing networks. You can't put on a router the same subnet on both sides. That would make it a switch, which operates at a different layer of the OSI model. The router operates at the third level of the OSI model, which is the part where we use for routers to separate our networks. You could also use a layer 3 switch, because remember, the router sits at the layer 3 of the OSI model. So we could use a layer 3 switch using virtual local area networks. So we could use a physical router between each subnet. That would make it a subnetwork of 3. Or we could take a layer 3 switch and have it all done through software inside the switch. So instead of being 3 different local area networks, they're 3 different virtual local area networks. So anytime you do this with a layer 3 switch, they change from subnetworks to VLANs. It's the same thing. It's just 2 different terms because one's being done through a switch and one's being done through a router. So we use a software switch in virtual machines. And the layer 3 switch runs at the network layer of the OSI model. It goes physical, data link, and then network. And network is where Internet Protocol lives. So remember TCP over IP? IP lives at layer 3. Where do you think TCP lives? It lives at layer 4 because TCP is over IP. Let's talk about those subnet masks. What do? Well, they separate networks on the left from hosts on the right. Networks appear on the left side and hosts appear on the right side. It's a total sliding scale. You can slide it one way or the other. If you want more hosts, you slide it to the left. If you want more networks, you slide it to the right. They're represented by contiguous ones and zeros, so you can't have any breaks between those ones and zeros. It either has to be all zeros on the right or all ones on the left. Each section has a value of 8. So in this case, if we see a CIDR value, of /24, we can see how that's spelled out as a subnet mask. Since each section has a value of 8, and we need to come up with a total of 32, 32 minus 24 is 8. So all we have to do is subtract 8 ones and come up with zeros on the right-hand side. Subnet mask's job is to change the amount of usable IP addresses. So let's look at an example. 192.168.1.0 with a CIDR value of /24, which we just talked about, allows us to use 254 addresses. But if we use that same number, 192.168.1.0, and we do a /28, we only have 14 addresses. Well, how does that happen? Let's see this spelled out a little bit better, where the numbers sort of line up to the subnet mask. The first 3 octets are networks, and that's from left to right. So again, networks are on the left. Hosts are on the right. The last 1 octet is for the hosts. Since each octet is worth 2 to the 8th power, because remember 8 times 4 is 32, then we have 2 to the 8th power equals 256 digits. We always start with 0. So that means we can go from 0 to 255. Remember, we need to subtract 2 numbers, the first one and the last one. The first one is a 0, the last one is 255. We need to subtract those 2 because they're unusable. So that means our usable addresses are 254, numbers 1 through 254. 0 is unusable and 255 is unusable. Let's do another example where we had the CIDR value of /28, where we had 14 usable IP addresses. Once again, we start out with 192.168.1.0. We're going to use less of those. You can see here, if we do a /28, we're only going to add up to 240 instead of the 255. The first 3 octets are for networks, and the last octet is partially for networks, and the rest are for hosts. So if we add up that last octet of 240, and we add 15 of that, we get 255. And since we use binary instead of the power of 2, we only have to subtract 1 IP address. So 15 minus 1 equals 14 usable IP addresses, as you see on the left-hand side. It's okay that this is confusing. You just need to go through it enough times for it to make sense, and it will make sense. Once again, we move our mask over from the left to the right for more networks. We move it from right to left for more hosts. Here are our binary values. We see our 8 ones, and we see our values in the decimal from 1 to 28 from right to left. So we once again have the same IP address, 192.168.1.0. In binary, this is what that looks like. Remember, this is not a subnet mask, so you can have ones and zeros split up. So we have 192. That value is the last two numbers on the left. 128 plus 64 equals 192. The second octet, 168, we can see how that is added up. And then 1 is simple, of course, as well as 0 being simple. So that is that decimal number spelled out in binary. And we see we're now going to use a subnet mask of 24. So we're going to use a mask to separate the hosts from our networks. So here's our CIDR value of /24, 3 octets of 1s, 1 octet of 0s. 256, if we go 2 to the 8th power, minus 2, 1 for broadcast, 1 for network, we get 254 IP addresses. If we use binary and simply add up 1 plus 2 plus 4 plus 8, using the subnet mask of zeros on the right-hand side, when we would just subtract 1 IP address instead of 2. They both get you to the same place, they just do it in a slightly different way. So let's mask out the network. Once again, this is our IP address spelled out in binary. We have a mask of /28 this time. This is what a subnet mask of /28 looks like spelled out in binary. We have a decimal value of 1 plus 2 plus 4 plus 8 because that's the 4 zeros. That's what those add up to if we add up their values, 1, 2, 4, and 8. We see a half a block of octets of zeros on the right-hand side, those 4 zeros. And that means 4 bits. 28 plus 4 equals 32. So the subnet mask of /28 means we have 4 bits for the hosts and /28 bits for the networks. So let's mask that out once again. 8 plus 4 plus 2 plus 1. That's those 4 zeros. That equals 15. 15 minus 1 equals 14 usable IPs. Let's say we don't want to use the adding up of the binary numbers. Let's say we want to use the power of 2. So if we go to the power of 2, we do 2 to the 4th power, because remember, there's 4 numbers available there. And then we subtract 2 numbers from that, 1 for the broadcast, 1 for the network. 2 times 2 times 2 times 2 equals 16. Minus the 2 equals 14 usable IP addresses. We got to the same number, we just did it 2 different ways. So once again, networks on the left and hosts on the right. The 1 side of the mask can only be used for networks. The 0 side of the mask can only be used for hosts. So that's the way subnet masks work. They don't work the same as the IP address portion. Let's do another example using our 192.168.1.0 example. And once again, that's what it looks like in binary. But let's this time mask it out at a /20. And that's what 20 looks like. Now remember, we have to add up to 32. So 32 minus 20 equals 12. So we have to have 12 zeros on the right-hand side. 1.5 blocks of octets of zeros on the right-hand side that we can use for hosts. That means 12 bits. So if we use our mask, we would add up 1 plus 2 plus 4 plus 8, and we would keep doubling all the way until we got to the 12th bit, which would be 2048. Now if we add up 2048 plus 1024 and all the other numbers, we get to 4095. And we subtract minus 1, and that's because we did this by adding up using the numbers from right to left. So we have 4094 usable IPs. If we instead decide to use binary, we use 2 to the 12th power, it gives us 4096. And we subtract 2, and we get 4094. So once again, we have the same amount of usable IPs, whether we go to the power of 2 or just add up all the zeros. Not all IPs in a range are going to be usable for hosts or endpoints. Remember to subtract 2 from the total if you're adding up using binary. 1 for the subnet, also called the network, and the other one for the broadcast. If we grab the connection details from a Windows 10 computer, we see here a 192.168.15 network. And we can see that the subnet mask is 255.255.0.0. So this is a far greater amount of hosts than we've had in any previous example. We see our gateway is set to .1, our IP address is set to .2, and we're using an 8.8.8.8 Google DNS server. So how many usable IP addresses can we use for hosts here? Well, what's 2 to the 16th power? We're going to have 0 through 65, 535. In 2 to the 16th power, that really adds up to 65,536 addresses. In a standard /24 CIDR type of a network, 192.168.1.0 through 192.168.1.255, 0 is the subnet or network address. The base IP is going to be .0, and it is unusable for hosts. But we have 192.168.1.1 through 254. Those are all our usable IP addresses, except for the .255. That's our broadcast. It's used to find other computers, see where they are, what they're up to, what their hardware address is. So to recap, 192.168.1.0/24 CIDR, the subnet, 0, the usable range, 1 through 254, the broadcast, .255. And you're going to see the /24 in small networks more than you'll see anything else because it gives you a lot of hosts, but not a lot of complicated setup. At some point in your career, you're going to want to learn about supernetting so you can save yourself a lot of time when it comes to setting up routing and switching. Take a look at the graphic and we can see before and after supernetting. Supernetting helps with routing. It cuts down on the statements needed when creating routes. And it makes no changes to the actual subnets or IP addresses themselves. It just helps when you set up a router or firewall or switch. Let's see how it does that using our graphic where we have 3 different networks with all a /29 CIDR setup, which means that each of them has 6 usable addresses. In the middle, we have either a router or a layer 3 switch. Either one of those will work for this particular scenario. Let's take a look at some routing statements. In this case, we're using a Cisco router, and we see route add 192.168.1.0, and then we see the mask, which is a /29, represented by 255.255.255.248. And then the last thing we see here is a 192.168.5.1, and that is our gateway. So basically it means that we're currently on the .5 network, and we're trying to get to the .1 network. So in order to get that, we need to set up a gateway. In this case, our router is the gateway. On one side of the router is .5, and on the other side of the router is .1. So this tells us how to get from one place to another. So we need to add these commands, route add 192.168.1.8 in this case, where we're trying to get to the 1.8 subnet, and again, /29, and the gateway 5.1. And then we have our third route, which is to the 1.16 network. So these all have to do with that same graphic that we showed with 3 different networks. And we add these different routes to get to those different networks, and they're all going to pass through the 5.1 router. Instead of adding 3 different commands, we can do it with just a single command. So we would just add the route add 192.168.1.0, and instead of doing a /29, we do a /24 CIDR, which basically means that it covers all 254 addresses. So we can pass all traffic for those 3 different subnets using a single command. This can be done either on a router or a firewall, but you might find that the syntax or the way we write out the commands might be slightly different. It also varies by different versions of the iOS as well. When learning subnetting and TCP/IP and routing and switching, we talk a lot about network and broadcast IPs. Those are the first and last IPs in any type of subnet or subnetwork. The network address is the first address in the network, and it's used for identifying the network segment. All the IP addresses using this same network address are in the same network segment. Because network addresses are the first address in the network, it cannot be a random IP address. It must match with the network mask in a binary view. If we look at a subnet mask, we notice that the last bits in the network address must all be zeros on the right-hand side. The network address cannot be used by a host. And remember, a host is the same as an endpoint or a PC, tablet, or phone, or any other device that has an IP address on it. A broadcast address is a little bit different. It's the last address in a network. And it's used for addressing all the nodes in the network at the same time. It means that the IP packet, where the destination and broadcast address is going to be sent to all nodes of the IP network. It's really important for remote announcements in the network segment. In some cases, it's used for attacking purposes by hackers, and it can also cause issues with filling up network bandwidth. The broadcast address is also unusable by any hosts. Let's talk about a real-world example with these different types of IP addresses. We'll talk about the network address. If you've ever shared a network printer, for example, you can have a problem when many people send print jobs to this printer all at once. So how do you separate the jobs from each other? You could use a blank separator page as an option in the printer setup. This puts a blank page between each job. It makes it so much easier to find your job when you can separate it out from other jobs sitting in the completed tray. Well, the network address can be used in the same way. Think of it as your separator page when you have many different subnets that all start with the same starting octets. By adding the separation, you can see when it's local to you and when it's remote. If it's remote, then it's going to require a router for you to get from your local network address to the remote one. Broadcast addresses represent all devices of the network. If an IP packet is sent on a broadcast address, it's intended for all the devices on that network. It's always the last IP in the subnet. By sending a packet to everyone, you're trying to locate a specific computer in your network. Once this is found, the network switch will memorize it, so the next time you need to find that same server or computer, it won't need to send a broadcast packet, and that will speed up your network. Let's take a look on an actual subnet, which one is the network and which one is the broadcast. If we take our example of 192.168.1.0 CIDR/29, that means that the .0 is your network address. Then you've got the 192.168.1 through 6. Those are your usable addresses. Finally, we have the broadcast address, 192.168.1.7. 1.8 will start this all over again. 1.8 will be a whole new network with a block of usable IP addresses and a broadcast IP address at the end. Network and broadcast IP addresses are a necessary part of any subnet in an IP network, and now that you know where they belong, it helps you determine what IP addresses are usable for hosts and which of these are used for other purposes. Let's take a look at the OSI model. And a lot of times people can spend weeks or months studying this, but there's really not that much you need to know when it comes to the Network Plus test. You just need to understand what the 7 layers are and what it is that they do. If you take a look at the right-hand side, you see it starts with the application and goes all the way down to the physical. So if I were to send a data packet, say an email for instance, from one computer to another, I would send that data, it would go through the application layer all the way down through the 7 layers to the physical, and then when it gets to the other computer, it would start at the physical and end up at the application and then get delivered to the computer. We also see that the OSI model is split between the upper layer and the transport service. So there's 2 basic sections of our OSI model. The upper layer includes the application, presentation, and session, and the transport service includes transport through physical. There are 7 layers, as I mentioned, and the data travels between more than one device. And each one of these 7 layers has a job. So let's talk about what each one of those layers' jobs are. We'll start at the bottom, layers 1 and 2, physical and data link. As mentioned, the first one is the physical layer, and it includes several different types of physical devices because this is the physical layer. An example would be cables. So if you plug an Ethernet cable into an Ethernet port on a network card on a computer, that's the physical layer of the OSI model. The network card itself is also part of the physical layer. Another part of the physical layer has to do a little bit with software. So if you were to do a loopback test, basically pinging 127.0.0.1, which is a special IP address designed just for the loopback, then you would be able to see that that's at the physical layer. It tests the physical layer itself. If you get a response, then that means that the network card is operating properly. So if you're having problems connecting to another computer, it's going to be somewhere else other than the loopback itself. And that's because we sent data to the network card and it sent it back to us. So we know it's working. A long time ago, we used to connect all of our computers to what's called a hub. And a hub operated at the physical layer. Sometimes we call it a dumb switch, and that's because it doesn't have any type of memory whatsoever. When we would plug a computer into a hub, it would allow us to connect to other computers. The problem is that it was really slow, and that's because a hub would not operate at a layer that could memorize what's happening to it. So if I was on computer 1 trying to connect to computer 2, my computer 1 would send out a broadcast IP, and it would say, hey, where's computer 2? Computer 2 would respond, say, here I am, and then 1 and 2 would send the data back and forth. The next time that computer 1 wants to send data to computer 2 through a hub, there's no memory involved. So it says, hey, where's computer 2? It loses its memory because there is no memory. And let's say you were connecting 1,000 computers on hubs all to each other. That's a lot of broadcast, and that will really slow down a network. So what was invented was switching through the data link layer. So we moved the hub into the data link layer, and we change it now to be called a switch. And this includes two different parts. The data link layer does. We start with the Ethernet MAC address, and we also look at the frames. A frame is the unit of transmission in a link layer protocol. It consists of a link layer header followed by a packet. The header is basically the addressing. It says, hey, this is where I need to go. This is what I contain. And then it's followed by the packet of data itself, which is the information you're trying to send. Each frame is separated from the next frame by an interframe gap, and they never leave the local network. So frames are very important to be able to send data from one location to another. Now let's talk about the Ethernet MAC address. And again, both of these are at the data link layer, and they exist in switching, network switching. When a manufacturer creates a network card, it burns into the card a physical address called a media access control address. And that address is never changed. It is possible through software to make it emulate a different address, but there's no real reason to do that in most networks. And that's because there are so many different MAC addresses, being a 48-bit type of MAC address, that there's not a lot of chance that you're going to end up with a network with more than one having the exact same address. And also, every manufacturer's first 4 bits of an address are made by the manufacturer itself. So those first 4 bits identify the vendor or the manufacturer of the card. So what a switch does is it allows us to have a memory of the MAC address. So if computer 1 sends out a broadcast packet and says, where's computer number 2, it memorizes the MAC address, the physical address of computer number 1. When computer 2 responds, it memorizes the MAC address of computer 2. And therefore, things speed up because the next time we don't have to send out broadcast packets because the switch has remembered where computers 1 and 2 are. Both switches and bridges operate at the data link layer. Now, you've probably heard of a layer 3 switch, and that's because it operates at both the data link and network layer, which we'll talk about next. Layer 3 is the network layer. And this is where the Internet Protocol, or IP, actually lives. It allows us to route between networks. So when you have a router actually sits at the network layer. A switch operates at the data link layer. It only allows communication on the same network, whereas a network router will only allow communication on different networks. So on the data link layer, if you're trying to communicate on 192.168.1.0/24, then that's fine. It'll work great. But what if you want to communicate with 192.168.2.0/24? You got to have a router for that, or a layer 3 switch that can route between different networks that operates at both layers. This is where you're going to find your IP addresses sit. And again, when you talk about TCP over IP, it basically means that IP operates at one layer, but TCP operates at another layer, the one right above it. Routers and layer 3 switches, as mentioned before, both sit at the network layer. However, they do things a little bit differently. Routers route between subnets or subnetworks. However, layer 3 switches operate in something called virtual LANs or VLANs. They both do the same thing, they just call them different things. And that's because routers route between physical networks, whereas layer 3 switches route between virtual networks. It's all done through software, which is why it's called virtual. But once again, if we wanted to route between 192.168.1 and .2, we could use a layer 3 switch that has inter-VLAN capability where it can route between the different VLANs. And it'll work the same way as a router does. Layer 3 switches just use it using software. Let's talk about the transport layer. That's the next one. And TCP, UDP, and others all operate at the transport layer. So if we talk about TCP or UDP or GRE all operating over IP, they all sit at the transport layer. It runs right on top of IP addressing. So when you see TCP/IP, it literally is one on top of the other. However, more than one protocol can run over IP. We're just mainly familiar with TCP and UDP. TCP and UDP use what's called ports, and they operate at 2 to the 16th power. So both TCP and UDP have 65,535 ports. However, many other types of protocols may only have one port, such as GRE. GRE is used for tunneling. If I were to open up a port for HTTPS for Secure Socket Layer to do a secure transaction over the internet, I would be opening up TCP port 443. And the first 1,024 ports of both TCP and UDP are known as well-known ports. And that basically means that they were registered under various different types of vendors as well as services. So for instance, SMTP is the universal port for email. However, it can also be used for Active Directory replication and other things. So it doesn't have to be locked down just to email, but that is the universal understanding. Some TCP and UDP ports were registered by companies that no longer exist. So those ports can be used for other things. However, they're still registered under those port numbers. Now we're moving up to the session layer. And that's all about communication flow. You're not going to hear that much about the session layer or the upper layers of the OSI model as much, because not as much happens in those layers when it comes to infrastructure for an IT administrator. Mostly it's just the transport service has to do with infrastructure, getting data from one place to another. The session, application, and presentation layers have more to do with programmers. The upper layers basically are set up by the programmers, and how it is that that data is going to flow down to the transport service is all done through programming. The session layer starts, ends, and maintains a network session. So if you're about to send data from one computer to another, it's never going to happen without the session layer starting it and ending it and keeping it going. It also has to do with two other things: half and full duplex connectivity as well as tunneling. So for half and full duplex, basically that means half duplexing is going to send data one direction at a time. So if I need to communicate back and forth with computer 1 and computer 2, I can only do it one way at a time. I can send data from 1 to 2 and send data back from 2 to 1, but not at the same time. However, with full duplexing, it works differently. I can send and receive data at the same time, and that's because of the session layer. Tunneling is also started at the session layer. So if you're going to create, say, a VPN tunnel, for instance, it starts at the session layer and moves down through the transport and network layers. The presentation layer has more to do with the keyboard characters and encryption. So it doesn't have a lot to do in our OSI model, but those are pretty important things. So for instance, keyboard characters. Every time you go to type in your keyboard, it has to do with the presentation. You're presenting keyboard strokes onto your computer screen, and you need to have the presentation programming of an application to properly work. Encryption has to do, once again, with tunnels as well as encrypting data. So when we go to encrypt data, it has to do with the presentation layer. And encryption is all about hiding. So if you've seen any old movies that had a secret message in it, you had to decrypt it. And the decryption basically has a key. So for instance, if alphabet +1 is your key, then the letter A really means the letter B. So if you were to get a message that didn't make a lot of sense, but you knew it was alphabet +1, then you just move every letter forward one. So you understood the key, therefore you could understand the message. Nowadays we use keys that are 2048-bit or 4096-bit, so we have keys that only computers could possibly decrypt. And the presentation layer maintains all of that encryption. Layer 7, we finally get to layer 7. It has to do with applications. And this is where all programs are run. So for instance, if you were to use Microsoft Word, Excel, or any web browser, any application, any app on a computer, that is the application layer. And you can see why the upper layers all have to do with programming. So for instance, you're not going to be able to run an application without the presentation layer sending the keyboard strokes up to the application itself. And you're not going to be able to send that data anywhere unless you start your communication using the session layer. If we look at the Windows logs on a computer or a server, you're going to see a special section for the application. And that's great because it allows us to see any issues that have come up with the application layer all in a log that tells us what's happening with our applications. How do we see the data that's transporting from one computer to another? How can you tell which layer on which it runs? How do we see the data from each of the 7 layers? Can they be seen? Well, actually, yes, they can. The data from each of the 7 layers can be visually seen by using a protocol analyzer device or a software program installed on a computer. If you were to use a software program, an easy one to use would be the Wireshark free program, and you can download that from the internet. Being able to see the packets broken down into each of their layers can help us identify which layer may be causing a problem. And that way we can pinpoint our troubleshooting efforts. So for instance, if we're trying to send data from one location to another and it gets stuck, having a protocol analyzer will tell us at which layer it's stuck, and then we'll know, is it a physical layer? Is it a network layer? Maybe it's an application programming layer. And that protocol analyzer will help us determine that. We had a lot to talk about in this series of videos. We talked about an IP address, IPv4 structures, counting in binary, and then we talked all about how to break down an IP address and a network and subnet. And then we finished it off with our OSI model so you can understand where that data sits in each of the 7 layers. This is a big part of the Network Plus test. The Network Plus test will be a challenge for both new professionals as well as seasoned ones. Be sure to revisit these concepts multiple times before attempting the certification.